Hello, welcome to the presentation of our paper, Light Field Style Transfer with Local Angular Consistency, as part of the IEEE ICASSP 2021 conference. My name is Donal Egan, and this work was carried out by myself, Martin Oran, and Aliosa Smolik as part of the research project here at Trinity College Dublin. The motivation for our work was to extend existing neural-style transfer techniques for traditional two-dimensional images and apply them to four-dimensional light fields and to evaluate the results. Towards this, we will present our novel optimization-based method for light field style transfer. Our method iteratively propagates the style transfer from the central view of the light field to the outer views, while always ensuring that local angular consistency is preserved. We will also show that existing metrics are not suitable for quantitative evaluation of light field style transfer and propose a new metric for the task, which we call the Light Field Angular Consistency, or LFAC metric. First, we'll present some relevant background information and research. Light fields. While traditional two-dimensional images only capture the spatial intensity of the light rays, four-dimensional light fields also capture the angular direction of the rays. Light fields are commonly represented using the two-plane parameterization shown here, in which a ray of light is characterized by its intersection with two parallel planes, with one plane representing the spatial distribution of the light rays and the other plane representing the angular distribution of the rays. In practical terms, we can visualize a light field as a two-dimensional array of two-dimensional images. Each subimage, called a subaperture image, represents a two-dimensional slice of the light field over the spatial dimensions and captures the scene from a different viewpoint. Another useful way to visualize a light field is using epipolar plane images, where an epipolar plane image is a two-dimensional slice of the light field obtained by fixing one spatial and one angular dimension. Originally looked at for standard two-dimensional images, style transfer involves combining the content of one image, for example a photograph, with the style of another, for example a painting, to form a new image. To achieve this, we need to be able to define, separate, and extract the content and style of an image. The idea of neural style transfer was introduced by Gattis et al. Here, the outputs from the hidden layers of a deep convolutional neural network pre-trained for object recognition are used to construct content and style representations of an input image, which can then be in turn used to define content and style loss functions. Starting from white noise, a new stylized image X is generated through an optimization process, iteratively updating the image X using gradient descent so as to simultaneously minimize the content loss between X and the content image and the style loss between X and the style image. Following the success of style transfer for standard two-dimensional images, style transfer for other imaging modalities has also been looked at. For example, Ruder et al. Looked at video style transfer. This introduces a new requirement for temporal consistency between frames. They achieved this through the use of a new initialization method for the image optimization process, using a warped, previously stylized frame as opposed to white noise, and a temporal consistency loss function for penalizing deviations between consecutively stylized frames. Next, we will look at light field style transfer. Light field style transfer not only requires us to render aesthetically pleasing style transfer for each subaperture image of the light field, but also to preserve the angular structure of the light field. There is very little previous work on light field style transfer. The first paper on the topic was recently published by Hart et al. Their method builds upon neural style transfer methods for stereoscopic images. For each viewpoint, only a pairwise angular consistency between that view and the center view of the light field is enforced. This is okay for light fields with a very small disparity range, which they use as their test material. However, it is less appropriate for sparser light fields. We will see that our approach enforces local angular consistency between neighboring viewpoints, thus making our approach more adapted to sparsely sampled light fields. As well as the existing light field style transfer approach of Hart et al., we also evaluate our proposed approach against two baseline methods. The first is to simply apply the image optimization approach of Gattis et al. To each light field view independently. This approach takes no account of the light field's angular structure. The second baseline is to create a pseudo video from the light field viewpoints and to apply video style transfer method of Ruder et al. Here we have some necessary notation for the next few slides. LST denotes a viewpoint in the original light field. IS denotes the style image. L superscript S, ST denotes a viewpoint in the stylized light field. Omega represents a function that warps a given image according to the optical flow between two viewpoints on the original light field. C are per pixel weights defined to be 0 for disoccluded points between the original light field viewpoints ls prime, t prime, and LST, and 1 elsewhere. The main idea of our proposed approach is to adapt the previously mentioned video style transfer approach of Ruder et al. To light fields by iteratively propagating the style outwards from the central view while always ensuring angular consistency with previously stylized views is preserved. We achieved this through the introduction of a new initialization method for the image optimization process together with a new angular loss function. The basic algorithm is shown here. First, the center viewpoint is stylized. Next, viewpoints surrounding the center viewpoint are stylized while preserving angular consistency with the central viewpoint. Then, the next most outer viewpoints are stylized while preserving local angular consistency with neighboring viewpoints stylized at the previous step. This third step is repeated until the entire light field has been stylized. Next, we'll describe our new initialization process and angular loss function. The central view is simply stylized using the single image style transfer approach of Gattis et al. And is thus initialized to be white noise. The current slide illustrates the initialization process for all other light field viewpoints LST. We first take the set of previously stylized neighboring viewpoints. We warp each stylized view in this set according to the optical flow between the corresponding original unstylized view and the view to be stylized. We then initialize the viewpoint being stylized to be a weighted sum of these warped stylized views. The weights W are computed so as to give more importance to angularly close viewpoints, and further details on how they are derived can be found in our paper. We'll look at our angular loss function. It is designed so as to penalize deviations between neighboring stylized views of the light field. The current slide shows its construction for a sample viewpoint. Again, we take the set of previously stylized neighboring viewpoints. For each stylized viewpoint in this set, we warp it according to the optical flow between the corresponding original unstylized view and the view to be stylized. We then take the pixel-wise squared summed error between this warped stylized view and the viewpoint being stylized. This pixel-wise sum is weighted by the per pixel weight C, which are defined to be 0 for disoccluded regions between the corresponding original unstylized views and 1 elsewhere. Thus, the weights C ensure that disoccluded regions between neighboring views are excluded from the penalizer. This is repeated for each previously stylized neighboring viewpoint and the results sum to get the total angular loss for the current viewpoint. Finally, to stylize a light field view LST, we first initialize it according to the method laid out on the previous slide. We then use gradient descent to iteratively update the stylized view so as to minimize the total loss function shown here, where the content and stylized losses are as previously mentioned. Together, our new initialization method and angular loss function help to preserve the angular structure of the light field during the stylization process. Next, we'll look at evaluation methods and results. Given the subjective nature of evaluating stylization itself, we focus on evaluating the angular consistency of the stylized light fields. One way of doing this is to use the disparity mean square error. That is, to compare the disparity map estimated from the stylized light field with the disparity map estimated from the original light field. Another possibility is the light field epipolar consistency, or LFEC metric, initially proposed by Dabbit et al. To evaluate angular consistency for light field video interpolation. However, we'll see that neither of these metrics accurately reflects the observed visual results. While they are able to correctly discriminate between results when there is an obvious gap in quality, for example, between the image baseline method and our method, this is not the case when results are more comparable. For example, when comparing our method with that of Hart et al. The LFEC metric backwarps the light field viewpoints to the central viewpoint to compute a variance map, which is then used in a PSNR-like computation to output a metric score. However, backwarping to the center view cannot take into account disocclusions far from the center. Thus, we propose a variation of the LFEC metric, which we call the light field angular consistency, or LFAC metric, which uses local angular variance maps to better incorporate the local angular consistency of the light field. The explicit formulation of the metric is shown here. Next, we'll have a visual and quantitative evaluation for some examples, light fields, and styles. From all of the visual results, we can clearly see that the angular structure of the light field is completely destroyed with the image baseline method. The video baseline greatly improves on this, but the angular consistency is still only preserved along the snake-like path used to create the pseudo-video. It is clear that both our method and the method of Hart et al. Significantly outperform the two baseline methods. All three quantitative metrics reflect these observations. However, when scanning the stylized viewpoints as seen on the top row here, we observe less artifacts in our method, especially in viewpoints further from the center than in the method of Hart et al. This is as a result of our method enforcing local angular consistency as opposed to Hart et al.'s method, which only enforces angular consistency with the central view. However, the only metric which captures this observation is the proposed LFAEC metric. Similar observations can be made for this light field and style. When comparing the stylized viewpoints here on the top row and the stacked EPIs for our method and that of Hart et al.'s with the original light field, it is clear that our method has better preserved the angular structure of the light field. Again, the only quantitative metric which reflects these observations is the LFAC. The same observations discussed above also apply to this light field and style. The visual results suggest that our method is best at preserving the angular structure. However, our proposed LFAC metric gives a higher score to the method of Hart et al. Notably, the disparity range of this light field is much smaller than that of the previous two examples. The final example light field has the lowest disparity range. On visual observation, there is little noticeable difference between the two light field style transfer approaches. All three quantitative metrics give a better score to the method of Hart et al. From the four light fields we have looked at, visual observation suggests that our method is better than Hart et al.'s for light fields with a large disparity range, while there is little noticeable difference between the methods for light fields with a small disparity range. While our proposed LFAC metric is better at capturing these observations than previously existing metrics, it is still ambiguous in some cases. More results are visible in both the paper and on the project webpage. So, in this paper, we introduced a new optimization-based approach for light field style transfer. Our approach enforces local angular consistency between the light field views through our new initialization method and angular loss function for the optimization process. Our qualitative assessment shows that our approach at least matches the quality of existing light field style transfer methods when applied to dense light fields and outperforms them when applied to sparser light fields. We also show that existing metrics are not suitable for quantitative evaluation of light field style transfer as they do not reflect the observed visual results. Towards this, we proposed a new metric called the light field angular consistency or LFAC metric. The LFAC better reflects the observed results in some cases, especially for sparser light fields, but it also remains ambiguous in other cases. These findings motivate future work where novel metrics for light field style transfer need to be investigated and compared to subjective evaluations. Thank you for watching.